teeth together. That's fine. You do that slowly. Now relax. Relax your jaw.
Computers have been used in medicine for a long time. But here in University College Hospital, they're developing a new and unusual application. This patient has a badly formed jaw, which is going to be corrected by surgery.
Which part of your face do you think is wrong?
Upper jaw, I think.
Okay.
This is the original tracing of the X-ray.
We can see a small upper jaw, a relatively large lower jaw.
The medical team use X-rays to work out how much to move the bones and predict what the patient is going to look like.
Downwards and forwards, that lip will unfold,
yes,
and we'll have quite a nice long lip. This is what's happened. This red outline is where the lower jaw will be in relation to the new position of the upper jaw, which is the...
This procedure is very difficult because a face is a three-dimensional object and the X-ray is only a flat representation. Nearby at the Slade School of Art, a powerful mini-computer will soon help this process. From this demonstration head with a real skull inside, a model is produced by the computer which uses data taken from these special X-ray pictures. Real patients will be scanned by harmless beams of light. Even using a relatively large computer, this picture takes a long time to draw. The machine has to work out which pieces can be seen and which are hidden from view. It uses triangles to make up the complicated picture of the head. If we enlarge the picture, we can eventually see the smallest point the computer can control. This is called a pixel. The color and brightness of each pixel can be individually controlled. An enormous amount of information is displayed on the screen, making the picture look surprisingly real. Because a complete model of the head is contained in the computer's memory, we can choose to view it from any angle. Eventually, the medical team will use this system to carry out trial operations and show patients what they're going to look like before they enter a real operating theatre. Well, the design for that head was created using a fairly large computer. But today, even the humblest personal micro is capable of displaying graphics. In other words, pictures. And many of the principles are the same. But even if you look at a single character on the screen, it's made up of lots of dots or pixels. Here's a magnified view, and you can see the dots. In a way, characters are pictures themselves. To help me look at the principles behind the different ways that different micros handle graphics, I've got John Coll, who's a wide experience in graphics. There are two ways in which this handles graphics, aren't there?
That's right. The graphics can be displayed either as characters or in high-resolution graphics. First of all, let me explain a bit about the character graphics. I've got a model here which represents part of the screen, and the screen is split up into 40 columns across and 25 columns down. And into each position, you can place a character. I've got a pack of cards, and those represent the characters that are available on this micro. There are, in fact, 256 different characters. We've got characters like, you'll be surprised to know, M, A, C, and all the uppercase letters, all the lowercase letters, and some punctuation marks, things like that. And as well as those defined characters, we've got 128 spare spaces which are actually undefined. Now, each character has got a code, and in fact, small a is code 97. That's known as the ASCII code of lowercase a.
That's the American standard code for information interchange.
That's right.
I remembered it.
Very well, good. Yes, all computers really use the ASCII code. It's understood that 97 represents a small a by virtually every computer.
And we can show it on the machine.
That's right. We can ask the computer to print out CHR $97, and it knows that that's a small a.
That's asking to print the character whose ASCII code is 97.
That's right.
And it's the same as saying print in inverted commas small a.
That's right, exactly. Print, inverted commas, small a, close inverted commas, and it has exactly the same effect. The computer understands that 97 is small a.
So that top instruction really enables us to print characters that we haven't got on the keyboard itself.
That's right. I've got a program in here which shows quite a lot of the ASCII character set spread out. There are a set of numbers and a set of characters. The numbers on the left are the ASCII codes, and next to each ASCII code is the letter or the character that code stands for.
Yeah, I can see the A up there on the top of the screen.
That's right, 97. Let's have a look at that on the enlarged grid. That's now plotting the pattern of pixels that correspond to the letter A, and you'll see that there are 8 points across and 8 points down. A total of 64 pixels are used to make up that lowercase a.
So if you wanted to use one of your blank cards, how would you design something on a blank card?
Well, we can use this program to do so. Let's move up to the ASCII codes which are blank. That's above 128. You can see none of them are defined at all at the moment.
That's not the same in all micros, though, is it?
That's right. Some micros, the things are already defined. Some of our cards on our micro are blank, got nothing on them at all. But, I've got here some other shapes, and for example, on the PET and other computers, there's some predefined shapes, like a triangle or a striped line or a diamond shape, and those are placed in ASCII codes above 128. On ours, codes above 128 are completely blank. In fact, I've got here a defined shape of a little man, which we could program into one of the characters. So let's do that into character 230, for example. Clear it, select character 230, and now it's ready to let me copy the dots from the card into the computer. So I'll move a little cursor across, and we want that pixel illuminated, and that one, and that one. Down to the next line, and this is part of his head. I can just turn the pixel on by pressing the space bar.
That's a special program that's been written for us. If you had to do it yourself, you could do it yourself, but it would be rather more tricky.
Yes, indeed. It's useful to have a program to be able to do it.
Yes.
Right, bit of body in there. So what we're doing is creating character 230, storing it in the computer's memory, and the computer, when I finish this, will know that character 230, ASCII code 230, is to be that shape, that image, that character.
So we can use the print CHR dollar.
That's right.
We'll do it.
Clear the screen and tell the computer to print CHR $230. There it is.
There's the little man. Well, can we move into the middle of the screen?
Yes, you can print the character anywhere you like on the screen, and there's a quite simple command: print tab. Now, tab is the command which says where you want it, and the screen, as you remember, is 40 positions across. So if we want to print something roughly in the middle line of the screen, we have to say 20 positions across, and then we have to tell it how far down. Let's say go 16 lines down, and that's given the position. Now we have to say what character we want to print. Again, 230, the little man.
Oh, there it is
And he
again.
appears. That's right. Well, it's a bit boring stuck there in one place. I can actually write a little program to print him all over the screen. Little 3-line program, quite simple. So 10, line 10. Print, and let's have it at some random position across. RND brackets 30. That will give me a random horizontal position up to column 30. And let's choose some random position down the screen, somewhere in the first 20 lines. And at that position, we'll print CHR $230, the little man. That's the first thing. Let's change his color as well. We could color random 3. That means some random color. It's actually going to produce it either in red or yellow or white. And that will only print one man at some random position. If we want to go around again and print lots of men, we have to put at line 30, that horrible phrase, go to, but go back to line 10, and that'll send the program round and round again.
I've got a feeling you really enjoy programming this machine.
No, I really hate it, honestly, mate. Clear screen, and run that program.
Oh, there it is.
Right, lots of men, different colours, different positions on the screen.
Well, it's not quite animation. Can we actually make him move around?
Yes, you can. To do that, you have to have a set of characters with a man in different positions, and we've actually got them programmed in already. You can see 3 characters here. Position 230, he's standing. 231, he's standing up with his legs together. And 232, halfway flying through the air. So if we actually print those one after the other, we can make him appear to move.
Oh, yes. Well, is the code very complex for that?
No, it's quite a simple little program. I'll list it out for you. That's the total program to do that. I'll just explain it. The top section of the program here is a repeat until loop, and it goes round and round that many times, doing the following. First of all, print at that position on the screen the first little character, proc delay. Now that means have a small delay as a procedure to develop a very small delay so that we can actually see him before we then print in the same position the man in a second moving position. This
Otherwise
time
it
it is,
would move too quickly if we didn't put the delay in.
that's right, you wouldn't be able to see anything, just a blur on the screen. Another small delay, and this time number 232, which is him right high in the air. Proc delay, another delay. And down below here, we've got the procedure defined. Define the procedure called delay. We've got a clock inside this thing, rather like a stopwatch. And this, first of all, sets the stopwatch to 0, and then gets it running, and it says repeat nothing at all until time is greater than 20 hundredths of a second, or until 0.2 of a second has elapsed. So it whizzes round here for 0.2 of a second, and then end proc, it comes back to that point with the clock set at 0.2 seconds.
What's the meaning of this until time is greater than 10,000?
Well, that until is part of this repeat until loop. It goes round here, waiting for the time to get up to 100 seconds. Of course, it'll never actually get there because the clock, the stopwatch, keeps getting reset by proc delay, and it actually never gets above 0.2 seconds. So really, it just keeps going round and round this, and that really means repeat forever.
Oh, let's have a look at him again.
All right. That's the little man.
Well, it's pretty small. I guess if you wanted to use something bigger, you'd have to move several characters together at the same time. Is that possible?
Yes, it is. I've got a program here which will do that. This program actually illustrates two types of graphics. It's got both high-resolution graphics, which we've got on the screen at the moment, and it's drawing some grass and some flowers. And then it uses character graphics, in fact 4 characters joined up together, to produce a bee whizzing around. Now you can see 2 bees on the screen, third one appears. Let's stop the program there, and we can have a look at one particular bee, and that particular bee is actually made up of 4 separate characters, but joined together. And those 4 characters I've got mapped out on these cards. Let's show you how the bee is built up. There's the top left of the bee, the top right, the other bit, and the last bit of the bee. And that group of 4 characters is what was used to draw the bee. Now those 4 characters are moved around the screen together. You know, it whizzes around the screen, buzzing as it goes. And in fact, you just use the print tab statement to print those group of 4 characters on the screen at any position you want.
Well, the bees are quite good fun, but they're not really high-resolution graphics, are
No, they aren't. They're drawn in character graphics. But even with character graphics, you can actually do some quite respectable things. You can draw some quite respectable and useful programs. Okay, so this is using the low-resolution character graphics, but even so, you can see that we can get some quite reasonable effects.
It still seems to be a lot better than you are at it.
True.
Well, let's take a look at what we mean by high and low resolution. Look at this photograph. It's been broken down into 80 squares, which are either white or black. So it's got 80 bits of information in it. See if you can guess what it is. Each time we're doubling the number of bits, doubling the amount of information in it. That's about the level you get on Prestel or CFAX. Now we begin to really recognize it, and we're putting more information in now by producing greys. It won't get any sharper, but it will produce grey colours. And finally, we shall get a full colour picture, and it takes about 5 million bits of information to display that colour picture, and it isn't even moving. Well, that's the 80-bit picture, and we've doubled them up there to 160, which is about 20, it's exactly 20 bytes, and you can't obviously recognise it. Here we've jumped to 80 bytes, it's still not recognisable. And here we're into about 1,000 bytes, where we can begin to represent it on these small micros.
That's right. What we've tried to do is to draw a circle on each of these micros, and this group here is just using character graphics, so it doesn't show up very clearly. The best we can do is to display a single character to build up this circular image.
That's about the level you'd expect on Prestel or CFAX and so on.
That's right.
So you can begin to recognise what it is.
But the definition isn't very good.
No. This is what I call medium resolution graphics, yes.
That's right, but one has to be a bit careful. On some of these computers, really, they're described as high-resolution graphics, but if you're used to using a really big machine, then you might only regard this as medium resolution. That's a better phrase.
But they're high resolution compared with the actual character graphics.
Very much so, and suddenly you can see a very clear image. There's a tremendous difference between this and character graphics. These here are using about 10k bytes for the display. So there's quite a lot of memory needed, even at that stage.
Well, the next step up isn't quite as significant as it was between the character graphics and so on, but you can see a difference here. We're using about 20 or 30,000 bytes of information, and it really is quite sharp, isn't it?
That's right. But of course, we're still only looking here at black and white graphics. We haven't yet introduced any colour into the image. Now, if you want to introduce colour, then you need to store a great deal more information. We've got here a model of the screen built up of a whole load of dots. Now, if we have a look at a single point here, instead of just needing one bit of memory for each pixel, you may need several bits, some to describe the colour of the image and some to describe its intensity. So for a full colour image, a lot more memory is needed.
So that's the payoff, if you like. If you have high-resolution graphics, you need a lot of memory. The character graphics, you need a small amount of memory.
That's right, that's right. Now, this model here represents the amount of memory that you've got available on an 8-bit micro. You have 64K of memory, so we've made that height represent the 64K of memory that you can address with an 8-bit micro. Now, you split that memory up between 3 areas. On one particular micro that this represents, the BBC micro, over half of the available memory is set aside for the basic and for the operating system. And that leaves less than 32K for the 2 other things, the screen display and the user's program. This screen display here is just a 1K display, it's a character display. And that leaves a great deal for the user program. That's quite acceptable, but of course you haven't got any good graphics. On the other hand, you can use medium resolution graphics, which take up a lot more memory, and that gives you less memory for the program. Still acceptable, perhaps. If you really want to use high resolution graphics, then you've got very little program space left, really, for the program, and that can be quite embarrassing.
Well, the obvious question to ask is, why does this take up so much, and what's the payoff there?
Well, yes, one of the other alternatives would be to cut down the size of the basic and the operating system, and that's quite a reasonable strategy. If you do that, then you'll have a less flexible and less powerful basic interpreter, but on the other hand, you will end up with more space available for your user program, and that may be a better solution in some cases.
Of course, you could add on another processor or even some more memory, I suppose.
There are other solutions, right.
John, many commands in BASIC are common, whichever micro you have, but I have a feeling with graphics that they're widely different. Is that the case?
That's right. There are some things that are common. For example, the screen is always treated as a piece of graph paper, with the origin, 00, down at the bottom left, and about 1,000 addressable points across and 1,000 numbers up, so that the X numbers go up to 1,000 and the Y numbers up to about 1,000. And in fact, 2 other things which are common are that you can take the pen that draws on the screen and you can move it on the screen.
Without drawing a line?
Without, that's right. Another thing which is very common is that you can draw a line on the screen. Those 2 are pretty common. Then on different micros you have different other additional commands. For example, you may have the command to go to another position, a 3rd point, and draw and fill in a triangle. Let me show you those on the micro.
That's rather like the triangle on the UCH head. Once you've got a triangle, you can really design any shape or any colour you like.
Yes, absolutely, because you can make a square or a circle from triangles. Let me show you, first of all, the command move. Let's move to a position somewhere near the middle of the screen. And on this micro, that's about 500 across and 500 points up. We don't see anything happen because we've moved the pen, we haven't actually drawn a line. The other command, which is fairly common, is the draw one. So let's draw to a position, say 1,000 across and 600 points up. And the computer on this one draws a line immediately. Now the third thing I'm going to show you is not common on all micros. We're going to draw this triangle, as you said. It's not very friendly on this machine, I'm afraid. It's the 85th option. It's plot 85. There are nearly 100 different things you can do. The 85th one is draw a triangle. And you have to say where to. Let's do it to position, say, 700 points across and maybe about 1,000 points up. Go. So that actually draws a triangle. Well, as you said, from a triangle you can build up almost any other shape, and I've got a program in here which will actually draw a pie chart, and that is a circle made up of different coloured segments.
Going out from the centre and drawing out little triangles.
That's right. Totally built up from triangles. Now, in fact, on some computers, for example the Sinclair Spectrum, there is actually a command to draw a circle straight away. without having to build it up from triangles, and that can be very useful on occasions.
So it's very much easier, I suppose.
That's right.
Well, some people are already exploiting the technology of high-resolution graphics and providing a new kind of service for companies and small businessmen who want to promote their products or display their sales figures in a more attractive way.
We're not limited to colours for background. We can change them at will.
This graphics studio is beginning to find computers very useful. The designer is using an electronic painting system to show representatives from Rolls-Royce how computers can produce advertising artwork. He uses a graphics tablet, an electronic drawing board, both to draw with and to control the functions of the machine.
Take a picture, which we can input from the camera.
Existing pictures can be digitized directly into the computer's memory from an ordinary black and white television camera. Then the image can be altered and coloured in many different ways. He can use 256 colours at the same time, selected from a palette of 16 million.
Colours to the different areas.
You see the logo on the side of the engine?
Yeah.
Would you be able to put that into a different colour so that that stands out?
Yes, we could.
From
the black and white.
main product?
A wide choice of different styles of paintbrush is also available.
For instance, if you say, well, this really should be a red wing, we could take a new colour altogether. Let's take one of the reds down here. We paint on.
The designer can do almost anything he could do with traditional paint and paper. Much of the studio's routine work, like drawing sophisticated business charts and diagrams, used to be very time-consuming and therefore expensive. Now it can be done quickly and cheaply with the finished artwork on paper or photographic film. So what sort of business graphics could you get on this machine?
Well, you can draw, for example, a bar chart. That's one of the very useful things in business, showing for every month of the year a graph showing the height, representing the number of sales or something like that.
You can actually
achieved in
almost
each
see it drawing in little triangles as it's going up.
That's right. All these are built up from a whole set of little triangles, yes. But really that's not very exciting. It's a bit slow. The program was written in BASIC, and there's an alternative way. You can actually write the program instead in a thing called machine code, and that enables you to do the same sort of thing, but to do it a great deal faster.
To do it, it will run faster, but in fact it'll take a lot longer to program.
Yes, absolutely. Well, here's a game that's written in machine code, and as you'll see, it's a lot faster. This time, the user-defined characters move around the screen very, very much more rapidly.
That's the little man is one character and the monster's one character.
That's right. Now, in something like this, speed is absolutely critical. And it might be that in your business program, speed was really critical too. But where it is, you can use machine code, and where speed is not so critical, you can work with BASIC.
But it usually takes a lot longer to write if you're using machine code.
Indeed, there are disadvantages as well as advantages.
Well, thank you very much, John. Later on in the series, we'll have a second look at computer graphics on the micro, when we'll investigate some more advanced techniques, including animation and computer-aided design. Until then, goodbye.
If you have a CFAX set as well as a BBC Micro, you'll find a version of the Jumping Man programme on CFAX page 702. For details of further information, including the BBC Micro computer system, the BBC Telesoftware service, associated correspondence courses, and information about other courses, computer clubs and other sources of local advice, please send a 12 inches by 9 inches addressed envelope with 16.5 postage to Broadcasting Support Services, P.O. Box 7, London W3 6XJ, and please indicate clearly what information is required. And now on BBC One, our weekly programme for those engaged in farming.